so so at first we do the classification trees. Okay, so then and then after the regression trees, classification. Regression tree. Then the bugging random forest. Boosting, I'm not exactly sure. We will cover it today. Bugging, yeah, probably not yet. But anyway, yeah. So we would cover these methods. So the classification trees and regression trees, it does not does not have much difference. Just response variables are different, and we use library tree. So you have to install this library. And the library ISLR, that we use some data sets within this library. Okay, so we use the car seats data set. So this is the data set for booster seats. It says that this is the artificial data, so not the real data. But I don't know why this is so detailed. So maybe it's actual data, but they have to hide some information. So that's why they claim it's artificial data. So the booster seats, the sales. This is the sales amount, and this is the competitors' pricing, and the income of the location of the store. And the advertising. Okay, so at first we have the 4 different kinds of booster seats, and the sales and the competitors' price and the income level of the location and the advertising amount and the population of the location and the price of that product and the shelf location. So I don't know, it's pretty subjective, but the bad, good, and the medium. So maybe it's advertised in a very high traffic area, or it's really at the corner of the store. So the shelf location, we have 3 categories. And the age, age is what? You can see the description by help car seats. So shelf location, age, average age of the local population. So that matters. So demographic matters for the sales of the booster seats. And this is the urban or not. And this is the made in the United States or not. So the US products and the international products are different in sales, possibly. So we have the 11 variables. So we want to predict basically sales. And the other 10 variables are predictors. But here, the classification trees, the demonstration for classification trees. So we just dichotomize this sales variable. So sales is more than 8 or less than 8. So yeah, car seats, sales. So you can make a histogram, then yeah, you can see this. So 8 is around the center, 5, yeah, maybe around 8 here. So just the high sales volume and low sales volume. So we want to distinguish these 2 groups. So maybe about 40% of the car seats sell more than the 8. I don't know, the unit is what? The car sales, the unit in 1,000. Yeah. Yeah, yeah. So we want to dichotomize. So this is the high sales and this is low sales. So that we want to define the variable high. This is car seats. Sales is larger than 8. Yeah, actually, just the car seats sales larger than 8 is sufficient. But here I just make this as a factor variable. So if higher than 8, sales is higher than 8, then the yes, then lower than or equal to 8, then no for this variable. So this is the binary variable whose value is either yes or no. And high as a factor. So it's the character variable. So that means that we have 3 yeses, but these are not recognized as the same value in R. So if we make it as factor, then almost it looks same, but the R recognizes that the first, second, third, and 6 observations are the same, have the same value for this variable. Okay, so now that we combine this data set, this new variable with original data set, so data frame, car seats. High. So we add the high sales. And we want to exclude this sales variable. So we don't use this. We only focus on this high variable. So we exclude sales. So this is this. So you can see the structure of this here. So we add another variable here, and we don't have the sales variable anymore. Then we remove high because we have now the data frame D, and okay, so we define the high variable first. Then within data set D, that we have the competitors, price, and so on, and also sales. High. So this high is duplicated. So high as a single object and high within data frame D. So we want to erase this the first one so that we remove high. Okay, so remove. Then we attach D. Then the tree classification by tree is done by the same format as usual linear regression with this tree function. So tree and response variable and the predictor variables and data D. So if we put dot, basically all variables except for this variable will be the predictors. So we have the 10 predictors, the competitors' price, income, advertising, population, and so on. Maybe 9. So 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. Yeah, 10. So now that we have the tree regression result, this is very short summary of the tree. So we have the 8 variables used, and this is the residual mean deviance. So it's a kind of the likelihood. And the number of terminal nodes, the 27. So it's very detailed tree. And the misclassification error is 9%. So what kind of tree it makes? We can type plot of tree. Then, okay, so it does not make much sense, but this is the tree. So we want to definitely see the description. So what variable is used to make the first split and so on. So we want to add the explanation, and that is done by text, the TR1. The pretty is some format option for classification variables. I mean the factor variables. Then CX is the font size, overall font size. So then you can see this. So this means that the shelf location is most important to determine whether or not sales is high. That sounds reasonable. If the booster seats are just in front of the the center of the store, then it sells more. And the shelf location, but or medium is here. If the shelf location is very good, then probably sales is higher. It depends on the each node, but and after that we decide competitors price. So shelf location is the bot to a medium. I think this is this one. And good here. Then if price is less than 135, then this way, and the more than 135, this one. So even price is higher, if income is higher, then still it sells well. If price is lower, then again, if it's made in US, then still it sells well. But if not in the US and the price is high, it does not sell well, and so on. So it's pretty intuitive to interpret. Yeah.
Sorry, Professor. In the first level, I think that price less than 135 and price less than 92.5 have some conflicts together, have in some range, they have conflicts together. They don't have?
Sorry, this price 135 and 109,
yes.
do you mean?
No. At the other level, yes, price. Yes.
Price 92.5. Yep.
Yes. So these two groups don't have any conflicts together.
No, we don't have. So basically, we split this into two. Maybe it's good to have some handwritten explanation. So yeah, so you can imagine that at first so we have maybe two-dimensional space, the plane, and we divide this by shelf location. Then after we divide by some so the vertical line, then for each piece is divided at different locations. So yeah, just a moment. Good. Okay. So okay, so yeah. Okay, yeah. So yeah, you can see that the shelf location. So we have the two axes. So this is the shelf location, and maybe we have three levels. So bad and the medium, and the good. And we have another one. Another one is price. Okay, so then the bad and medium and good. So we separated the plane into this, so two in this way. And if the shelf location is good, then the price less than 135 and more than 135. So we have this threshold and this threshold. So basically, we divide the original space into 135. We divide it into 4 areas. Okay, so that is the optimal in this estimation. So 1, 2, 3, 4. So we divide it into pieces in this way. And yeah, actually, on two-dimensional space, I cannot do more. We cannot describe the more nodes, but in this way, we can split it. Yep. So it does not contradict. Does this answer your question, or?
Yes, I just thought that maybe they have some overlap because less than 132.5 have some overlaps with 92.5, for example. But I think that I made a mistake. It's fine. I
Yeah,
understand.
so
It's fine.
right. So overlap, but we don't have any contradiction. Yep. Yep. Okay. So yep. Share.
Oh, I have a question.
Oh yeah, sure.
So do trees, do they normally, we'll say, like use price or a variable twice within like one?
Yeah, so
branch of
the many
tree?
times, yes. So yes.
Because I know the example in the textbook, it doesn't have that. So, or the
I
one we
see.
saw in lecture on Wednesday.
Oh, that may be right. So yeah, so we have the multiple ones. So you can think about, okay, so yeah, so yeah, so okay, so suppose we only have two variables, the shelf location and the price. Then okay, so and we split this the many times, then what happens? Okay, so 1, 2, 3, 4, then oh, I see. Yeah. Yeah, it's possible. It's possible that we have, yeah, so we have another split here maybe, and then another split here, and yes, another split here, possibly, and another split here. In that way, that we can split it into many parts. So yes, the one criterion that should be can be used multiple times. Yeah, so shelf location is good and the price is low, then it sells more. So that means probably maybe this and this and this area, maybe sales is good. And I don't know. And other places, no, that is possible way. Yeah, so multiple locations, the same variable multiple times is often the case. Or even one-dimensional case. Think about one-dimensional case. You may have to use the multiple times. So suppose we have x1 and we have So if categorical case, the y is categorical, then even if we have only two possible values. Yeah, then the first split is probably here, and the second split is here. So the same variable can be used twice. So at first, maybe x1 is less than 100, and the second x1 is less than 60. That is possible. And obviously, for regression problem, we really need the multiple split, even if the function is monotone. If x is here and y is here, and suppose we have linear regression type pattern, then what happens? At first, probably we split here, and maybe the level is here for larger than x is equal to 100, and probably lower than here for x is less than 100. But if we have another split, what happens? If we have another split, probably it separates the observations around here again, and maybe the level is here and here and here. Okay. So at first we divide the node by x is less than 100 or not. Then after that more than 100, actually again the x is less than 100, maybe 50. Yeah, that is certainly possible. Yeah. So one split is just another step function. So to represent complicated pattern or gradually changing pattern, we certainly need more than one split for the same variable. Okay, any other questions? If not, then we continue. Yeah, so this is the case, and yeah, I'm not exactly sure why do we have both. Yes, population is less than 207.5 and more than 207.5. Yeah, I think that this yeah, I think it's strange. So no, but basically we have to separate the cases to minimize the error size. Both are yes. Why this happens? This isn't really sure. Yeah, so this is the case. So if we skip the pretty is equal to 0, then how it looks like? How does this? Then here, yeah, so shelf location AC. So this cannot be interpreted. So probably we have A, B, C, and A and C we picked. So it's not really clear what it means. So pretty is equal to 0, then we can have the more appropriate label for factor variables. Yeah. Yeah, the shelf location. Shelf location. Yeah, so we have the 3 levels: bad, good, and medium, and we combined bad and medium to make the tree. Yeah. So we combined bad and medium, so that is probably the first one and the third one in alphabetical order. So that's why it says the shelf location AC, but A means bad and C means medium probably, but it's harder to see the meaning. So the pretty is equal to 0 option is more convenient. Okay, so now we will see how many observations are classified correctly based on this rule. And so basically we need the predicted value. So this tree is large, but this does not mean the classification is perfect. Yeah, so it stops at some point, so that's why the classification is not perfect. So if we make the arbitrarily larger tree, then we can do perfect split if we have many variables. But here, for example, the price is less than 109, and yes and no. But this group may consist of 5 observations, and this group may consist of 4 observations. Maybe 4 of the 5 is yes here, and maybe the 3 of the 4 is no here, but still the classification may not be perfect. So we want to count how many observations are classified correctly. So predictor tr1 type class. Then we see predicted class for all observations. So we have 400 observations. So so 400 the dimensional vector of no and yes. And now that we want to make the confusion matrix contingency table for here. So the $high. So this is the truth. So this is the truth. So actually there are 13 plus 151. So 164 observations with yes, and 236 observations of no. So 164 observations have high sales, and the 236 observations have low sales. And this is predicted value. So mostly it's predicted correctly, but this is the in-sample fit. So basically we use all observations and we calculated the fitted value and we compare it. So usually it works well. So if we have another data set and we apply the same model, then usually the error rate is much higher. Okay, so now we want to see what's the best size, I mean the best number of nodes for this tree. So this is probably too complicated, So in sample, by some algorithm, the tree grows up to this size, but probably this is too complicated, and the cross-validated error is smaller if tree is simpler. So we want to verify this. Yeah. So at first, we try the validation approach. So to optimize the number of nodes, actually, we have to do cross-validation. But before that, we do the validation approach to see what's the the size of error for test set. So we divide the original data set into two pieces: the training set and the test set. So at first, the index for training set. And the test set is the complement. So set difference of 100 to 400 to TRN. So TRN, so TRN is these observations, and the test set has these observations. So it's mutually the exclusive and exhaustive. So the first and the second observations in the test set, third observation, training set, fourth, fifth, sixth observation in test set, and so on. And both data sets have 200 observations. Yeah. And the so the original data set is D, so the training data set is the DTRN. So we picked up these indices, then that is the training data. And the test data, that we replace this by TST, then we get the test data. Then we fit tree, the same tree for training set. Okay. So 200 observations only. then if use this training set, still training set, then we do this in-sample data. We use the in-sample data, so the result should be similar to previous one. So the sample size is half of the 400, but so the table is similar. So last time that we have seen that the table is here. So in total that we have 400 observations and 36 are incorrect. So the misclassification rate is 9%. And here that we do basically the same thing, but for smaller sample size. So the 24 observations are misclassified out of 200. So 24 out of 200 is 12%. So slightly larger, possibly because the sample size is smaller, but it's similar. So how about test error? Test error. Maybe test predict TR2. New dataset TST, and the table test and the high TST, then this. Okay, so now this is the test error. I mean the test result, the result. This is the result for test dataset. And you can see that out of 200, actually the 49 are misclassified. So it's much larger than the before. Okay, so 49 over 200 is almost 24 point. Okay, so almost 1/4. So the misclassification rate is about 25%. So that's much smaller, much larger than the previous one. Previous one 12%, and all observations, 400 observation in training set, then misclassification error is 9%. So the 9% or 12%, it's similar, but the 25%, that's much larger. And this 25% is more realistic number for the error rate for new data set. So 25%. So now we want to see what's the optimal number of nodes. And we just set seed to get the same result always. Then we use the cv.tree function to optimize some hyperparameter. So TR2, so TR2 is the original tree for the test set, I think. So FUN. So there are several functions to optimize cross-validated error. So the cross-validation is a general method for prediction performance for new data set. And what criterion to use? So we may use some likelihood in the same way as logistic regression or misclassification rate. And this prune.misclass function measures the misclassification rate. So this 25% or 12%. So we want to optimize that number. So we want to minimize that number. Oh, sorry, this 22 out of 200 is 11%. I said 12%, but 11%. But anyway, so we want to optimize in this way. So misclassification, actually classified observation, number of observations. Okay, so then, so this is the result. So we have, this is the number of nodes, the size of the tree. And this is the DEV. So this is the misclassified observations. So TR2. Maybe summary of TR2. I think TR2 have 200 observations. 200 200 observations, and these are misclassified number of observations. So it's pretty large. So 68 is the minimum, and it's as large as 93. So 93 is actually the tree of size 1. So that means that we don't split any. Size is the size of the split. Maybe size of the split, so only one split maybe. So then 93 observations are misclassified, almost half, and 283 and so on. So basically we have help. So basically we have the 5. So just a moment. Cross validation to find the number of misclassified as a function of parameter k. And sorry, I'm not exactly sure and about this is the size of the tree of or the size of the node. One observation. Yeah. Yeah, I think that this is the size of the split. So the number of split. So it's the different from the number of nodes. Nodes is 2, I think. Yeah, because if we don't split, then anyway, then we cannot get any answer. So we have to classify everything in the same node. So, but still maybe 93. That's possible. No, just let me see. TRN, DTRN, classify. No and yes, 93. But anyway, so this is the cross-validated one, so that we cannot really see it. So this is the, I think the number of split that we have to, I have to check it again, but this is the number of split. If one split, the misclassification is 93 out of 200, so 46.5%. So if we have the 5 split, then we have the best answer. So this is the best point, probably. If we change the seed, then possibly the answer is different. So if set seed. Yeah, so it's different, but still we choose the same number. Okay, so this cross validation, actually the error is generally smaller, but if the size of the split is 5, then it's the best. So probably it's size of 5 is the best. Okay, so yes, and and this k is the parameter. So we have seen that we have penalty term for the size of the tree. And if k is larger, then we penalize large tree more. So that means the tree becomes smaller. So this is corresponding k. So if k is smaller, the size is larger. Yes, and the last time that we used the alpha, but it seems that we have the different scale. So this says the k is negative infinity. So probably this is exponential scale. So we have the penalty term. Oh, okay. So yeah. Yeah, so I believe that you are seeing slides. So yeah, we have penalty term here. Alpha is here, but the k is the exponential scale. So the negative infinity corresponds to alpha is equal to 0. So we don't penalize it at all. Yeah, so I believe that this is the maximum size set by some criterion, probably square root of n or something. So maybe not the, yeah, so the data set has 200 observations. So yeah, so this is probably the set maximum number. So if k is negative infinity, then we choose the largest tree. Then if k gets larger, then we choose smaller tree. And the optimal one is the one which minimizes the deviance. Actually, not deviance, actually the misclassified observations. So yeah, we have several possible ways for the loss function. So here we count the number of misclassified observations. If we use deviance, then we get deviance here. And actually the object always has the name DEV, even though this is the misclassified number of observations. Okay, so this is the way. So now we determine the size. Yeah. Yeah, you can make a graph of this if you wanna see it, but this is the optimal point. So now that we use only the 5 splits. So we define the tree with 5 splits as the TR, the 2P. So if you see TR2P, then you see this. So we have 200 observations at first. Then advertisement amount is less than 7.5 or more than 7.5. This is the first split. And the second split is price is more than 105.5 or less than 100.5. And the third one is this one. And the fourth one is this one. Sorry, so this is probably the number of nodes rather than number of splits. Sorry, so I said that the size means the number of splits, but actually this is the number of nodes. So we have 5 nodes. So we separate with the 4 criterion. So we have 5 nodes. Yeah, then you can see, for example, advertisement is less than 7.5 and the price is less than 100.5. Then it's why? Yeah, so this is yes for. It's hard to see. We have the 32 observations, and we have the 41.18. So yeah, probably 32 out of 41. Not sure. I don't know, but 65% of observations are yes. The 32 is the number of observations probably, and 41.18. I'm not exactly sure about this, but the 65% yes. but the price is more than 100.5, then the 84% no. So this is classified as yes, and this is classified as no, and so on.
Is the 41.1 the deviance?
Maybe. Yeah, sorry, I don't really know. Yeah, maybe that's true. Oh, deviance here. You mean? Oh, yeah, you're right. You're right. So y value. Yes, you're right. So deviance, yes. So this is the splitting rule, and this is number of observations, and this is deviance. Yeah. So what is the? Yeah. So the deviance. Yeah, maybe deviance. Yes, that's right. So even though we use the misclassified observations, so this is deviance. Yeah. But here the deviance, actually these are the misclassified number of observations. So I'm not exactly sure what this 41.18 means. So maybe deviance. At least some value of error function. And another way to specify the tree is by k. So this is the number of nodes, but this is the number of the parameter value k. So yeah, so I'm not yeah, so yeah, parameter value. So then TR to P2, probably this is the same. K is equal to 3. So the yeah, instead of specifying the size is 5, that we specify the parameter k. And actually this 5 corresponds to 2, but the k is some parameter value. So if we pick 3, then actually we get the same nodes. If we pick k is equal to 3.8, probably we choose this tree. So we can also determine the size of the tree by specifying this parameter k. Yeah, probably the alpha in this slide, number 5 in chapter 8, is e to the power k. But I'm not exactly sure what transformation they make. Probably alpha is equal to e to the power k, but I'm not exactly sure. So usually this parameter, so result isn't sensitive to this parameter. So if alpha is 1.5 times larger, probably the result does not change much. So using exponential scale makes more sense. And also, if we take the logarithm, then the k value is from negative infinity to positive infinity. That's easier to deal with compared to the non-negative value. Yeah. Yep. So. Yeah, misclassification. So that we use the different rules. So the misclassification rule, the TR to P3, then this is the same result as before. And we use misclassification rate as the error function, and we specify the parameter value k is equal to 3.0. But also we can do another method, the deviance. Then TL to P4, that we get this result. Yeah, advertisement. Oh, yeah, now we can see what this deviance means. So 138.9 is the same value. So yes, Raymond is right. So this is actually the deviance. Yeah. So this says deviance, but actually this is deviance. So any method that we have the same value. Yeah, but actually if we use deviance, the tree is much larger, it sounds. So why is so different? Because just the error function is different. So the scale of the error function is much different. So the k is equal to 3 with this loss function, and the k is equal to 3 for this loss function. Just it's entirely different issue. So yeah, so this k and this k are not comparable because yeah. Yeah, because yeah, so you can see that if error function, the size of the first term is different, if size of the first term is different, then the meaning of this parameter is totally different. So these two results are not comparable. But we choose k is equal to 3 for misclassification rate. So this is appropriate result, but this doesn't make much sense. If we use deviance, we have to optimize k again, and probably the optimal k is larger than 3. Okay, so now we optimized it so that we wanna make the test error. So we wanna calculate test error. So predict TR2P class seats TST type class error TR2P car seats undefined column selected TST. So car seats are the data frame. So we want to pick up these rows. So we specify rows by specifying indices. So this is the correct format. Then TR2P. So yeah. So we make the contingency table. The height. No, the height, not height, height. So TR2P. So the TR2. Oh, so I made a mistake. We have to define a table. So anyway, so this is the table. So this is the misclassified observations. So the misclassification rate is pretty large. So 73 out of 100, 200. So 73 over 200. So the 36.5% misclassification rate. Yeah. Yeah, so I think that we can use the TR1, so all 400 observations to do this. No, actually the TST. We optimize parameter with the training set. Then after that, we have to evaluate with the test set. So if we use the validation approach, still that this is the best way to do. If we use cross validation, we can just put all 400 observations and we can see the result. Then probably the performance is a little better because if 400 observations, for example, the tenfold cross validation, we use 90% of the data as training set, so 360 observations. So it's probably a little better. Okay, so next, if you don't have questions, do you have any? Okay, so now the regression tree. So library ISLR3 package we use. So since this is more quantitative, that we use the correlation plot function. And again, that we use the car seat data. And so now, yeah, structure of the car seats. So yeah, car seats, still we didn't change the data, right? Yeah, so that we defined the data frame D, but the car seats is remains as original. So the pairs function that shows the scatter plot, pairwise scatter plot. So car seats 1, 6, then you see. So this, so sales and the competitor's price, almost irrelevant probably, but you can see the price and sales. It's related. So price is higher, sales is lower. So it's clear. Possibly advertising, the more advertising, sales is higher. Population size, it seems it does not really matter. Maybe because the larger city have more stores. So yeah, so in this way that we can see. And there are also pairs, maybe that we use other variables. So sales is important. So we keep sales, then other variables, then you can see sales and the other variables, the shelf location. So still this is alphabetical order. So this is bad, good, and medium. So if the location is good, sales is significantly higher. And age, maybe higher age, the sales is lower. That's natural. If the most people are elderly, the booster seats do not sell. And educational level, almost irrelevant. And urban or not urban, maybe too many observations, I cannot really see the tendency. And US or not, maybe US products sells more than other products. Maybe home bias. So if some products are made in country you don't know, then maybe the people don't trust it. Okay, so yeah, now we want to see the correlation, but to see correlation, it's a problem if we have this the variable like this shelf location. So we wanna order these 3 categories in a reasonable way. So to do that, we can use the levels option in factor variable. So car seats, yeah, shelf location. So factor variable. So the car seats, shelf location, and we can specify levels, and bad, and the medium, and good. So in this way, that we can we cannot really. Okay, so car seats, shelf location is the factor of the car seats, the shelf location, and the levels, the C, but yeah, okay, so that we don't have this. Then yeah, then so the scatter plot looks differently. So you can see the shelf location is better. So this is bad, medium, and good. So we have positive relationship between shelf location and sales. Okay, so suppose that we want to further calculate the correlation coefficient, then everything has to be numeric. So car seats, shelf location, and the urban. Urban is either yes or no, but urban location or not, that we redefine this as numeric variable. Then now that we can use the correlation plot of the car seats. So correlation of car seats is a matrix. If we have 11 variables, then that is 11 by 11 matrix. But if we use the correlation plot, then we can make this. So these are variables, the sales and other variables. Then we have 11 variables, and this represents correlation. If correlation is 1, this is the dark blue, and the correlation is -1, dark red, and the in between, it's closer to white. So you can see the sales is highly correlated, positively correlated with shelf location, and slightly positively correlated with advertisement and whether or not it's made in US. And the negative correlation is price. That is reasonable. Higher price, lower sales. And higher age, lower sales. So you can see the relationship at a glance. Advertising and US, it's related. Maybe the foreign international products are not advertised heavily. So it may look fancier than just correlation matrix. Yeah, so you can also specify the option, the methods number, then you can get number. Methods number. Yeah, then you can see the number. If you like numbers, then yeah, it's clearer. So this is 0.55, 0.27, and so on. Yeah, and the regression tree. Oh, yeah, regression tree just works in the same way as the classification tree. Yeah, so I think it's we don't have time, but the next time that we discuss the regression tree and the random forest and the tree regression. So maybe today I discussed too many other things, but maybe the graphics are useful for final projects.